Hi everyone. Hello Yash. Hi Ajay. Hi everyone. Good evening. Okay. So today we will see geometry of SVD, which means that what is the geometrical interpretation of SVD, and then we will see 30 questions regarding the SVD. Okay. As I promised in the last class that we are going to do some practice question on SVD and then followed by a quiz. So tomorrow there will be a quiz. Okay. And that quiz is just based on SVD. Just based on SVD. Okay. So now let's just get started. Okay. So let's see that what is the geometry of SVD, right? So we have already seen that if a SVD is given to us, for example, let's suppose this is the SVD. Okay. Let's suppose this is A, and then let's suppose this is U, this is sigma, this is V transpose. Okay. We have already seen that initial R vectors, right? If the rank is R, then initial R vectors are in the column space. Okay. And the remaining, let's suppose, okay, if I talk about the null space, let me first talk about the null space. So these are the vectors which are in the null space, right? So we already talked about it. So is my voice clear or there is some echo? Are you getting some echo? Let me know. Or the voice is clear. Okay. Okay. Great. So basically, these are the R vectors which are in the column space, and these are the R vectors. Oh, sorry, n minus R vectors are in the null space, right? Is this clear to everyone? Why that is the case? Because because as we know that we have basically figured it out that if you multiply this SVD, okay, whatever the SVD given to you, if you multiply this and then you rewrite it, right? If you rewrite it, then we were getting something like this. See, we were getting A equal to U sigma V transpose, and then from here we were getting A equal to U sigma V inverse. Sorry, V inverse. I mean, V transpose and V inverse are same. From here, we were getting AV equal to U sigma. Is this almost similar to eigenvalue decomposition? Tell me. Is this almost similar to eigenvalue decomposition? Yes, right. In eigenvalue decomposition, what we have? We have AU or a some eigenvalue eigen vector matrix equal to U lambda, right? This was the eigenvalue decomposition. Do you remember this? How many of you remember? Okay, great. Right. So this formulation that we have arrived with, right? This is almost same as eigenvalue decomposition. And then here we used to write AX equal to lambda x, right? Here we are writing AV or AVI equal to sigma I UI, right? And that is for R vectors. And then for remaining n minus R, we were writing, you can say AVJ equal to 0 for J equal to, you can say R plus 1 to N, right? So these were the two set of equations that we have got. Now from these two set of equations, we have quickly identified that these U's are in the column space. And since we have R U's, that's why they are actually forming the basis, right? Because they are anyway linearly independent. So that's how we got this. And similarly, we got this null space. Now we argued once more, right? We argued something else, and then we figured out that okay, row space and null space are orthogonal to each other, right? So because row spaces and null space are orthogonal, and these are the orthogonal vector to the null space, and these are R vectors. And in the row space, anyway, we need. We have in the basis we have R vectors. So that's how we argued that this is the row space. And similarly, column space and null is, left null space is actually orthogonal. So that's why we argued that this is a left null space. Okay. Do you all agree with this? So basically, we figured out that how four fundamental subspaces are related to SVD. Okay, cool. Now, let's just see geometry of SVD, which means what this SVD is doing. Do you remember from the eigenvalue and eigenvector, class, I told one thing that let's suppose you have some vector, and let's suppose this is V. Then if you multiply this vector by some matrix, let's suppose A, then the vector that you are going to get, the resultant vector will be AV. So that vector will be rotated, right? Do you remember I told? And this vector right? This vector was V, but the new vector that you will be getting, new vector will look something like this. Let's suppose this is AV, right? Okay. So yeah, matrix job is ultimately to rotate the vector, maybe to scale little bit and like that, right? This is the job of a matrix. But now we want to break it down. Okay, with this geometry, we want to break this, multiplication down into three different multiplication, and then we want to see that what is happening. Is the idea clear? So what we want to do, we want to do the same thing, but we want to understand this same thing after some breakdown. So I can say one thing here, that let's just do the similar thing, but here I will be just breaking it down into three parts. Okay. So we will break this multiplication into three parts. So what are those parts? Can anyone tell me? What is the first matrix that I will be multiplying to V? What is the first matrix? If I see this as a terms of SVD, what is the first matrix that I will be multiplying to V? This vector, or maybe I can say this X. Yes. So I will be multiplying to V transpose, right? So let me just call this as X. Okay. So I will be basically first multiplying to V transpose, I think, right? Because what is A? As you know, that A is U sigma V transpose. So AX is nothing but, you can say AX is nothing but U sigma V transpose into X, right? So the first matrix that I will multiplying to V transpose, and then I will multiplying to sigma, then I will multiplying to U. Is this okay to everyone? Okay. So anyway, this U and V transpose, these both are the orthogonal matrix that you know, right? By the way, what is the property of orthogonal matrix? Sorry, orthonormal, right? So as you know, the property of orthonormal matrix. What is the property or the formula, whatever you like to say? Let's suppose X or maybe U or whatever, right? Let's suppose U is orthonormal. Then U into U transpose will be what? Yes, great. This is identity matrix, right? This is identity matrix. Or if you like, you can also say U transpose is nothing but U inverse, right? Or if you like, you can say U, and since U transpose and U inverse are same, so this is also identity, right? I mean, you multiply left, you multiply right, doesn't really matter, okay? Doesn't really matter. Okay. This is the first property. I mean, I can say just as a definition of the property, but now I will introduce you something more, very uh, I can say geometric property. Okay, so I want to introduce you some geometric property. What are the properties? Very interesting. The property says that orthonormal matrices, orthonormal matrices are length and angle preserving. What do I mean by that? I will just tell you. Okay, length and angle preserving. Okay. Okay. So what do I mean by that? Let me just tell you, and we will prove it. Okay, that orthonormal matrices are length and angle preserving. So see what I'm saying here is that let's suppose let's suppose you have some orthonormal matrix. Okay, let's suppose U. First, tell me, is this okay to write U into U transpose equal to identity? You take the determinant both sides. Determinant of identity is, I think, one, right? Everyone knows this. Okay. So from here, you can also say the determinant of U multiplied by determinant of U transpose. This is one. And since these two determinants are actually same, right? So from here you can say determinant of u whole square is actually 1. And from this, what you can say, determinant of u is either +1 or -1, right? So for any orthonormal matrix, the determinant is basically either +1 or -1, right? Okay. So here I want to prove something, that these are the length and angle preserving. So let's just first prove, okay, length preserving. What do I mean by that? It means that length, okay, length of x. You know what is the length of x? Is nothing but x1 square plus x2 square, like this, right? Okay. So basically, I want to prove that length of x, and if you multiply, let's suppose any orthonormal matrix, u, okay, and length of this vector are actually same. Okay, I want to prove this, that length of this and length of this is actually same. So this is the first property, okay, which is called length preserving. So basically, even if you multiply, right, any orthonormal matrix, then the length will be same. The second property that we want to prove is basically angle preserving. Okay. Second is angle preserving that we want to prove. So what does this angle preserving mean? Angle preserving. What does this mean? It means that, let's suppose these are the two vectors, okay, x and y. Okay, whatever is the angle between them, right? If you multiply, if you multiply some matrix, okay, some orthonormal matrix to them, then what will happen is that they might rotate, okay, I mean here and there they might rotate like this probably. Okay, so basically your new, let's suppose this is u, okay, u is the orthonormal matrix. Ux and uy will be slightly rotated, or maybe in with whatever angle, but the angle between x and y will not be changing. Okay, suppose this is x, this is y, the rotation will happen, but the angle will not change, which means if this angle is theta, okay, this is not true for any arbitrary matrix, but it is true for orthonormal matrix. If this angle is theta, this is also theta, which means for any arbitrary matrix, what may so happen, if you take this, okay, for any arbitrary matrix, what may so happen, if you take this, and then if you multiply, let's suppose y, uh some a, which is need not to be orthonormal, right? Need not to be orthonormal. If you multiply by some a, then what will happen? It may so happen that you might get, for example, this is a by, this is, for example, it might so happen, right? So this could be different, right? This need not to be x, to be theta, basically. Okay. But we want to prove that for orthonormal matrix u, this is this will not happen, which means the angle is same. So these are the two properties that we want to prove, and these two properties gets hold for any orthonormal matrix. Okay. So let's just see how to prove that it is a length preserving. Okay. So just let me know that if you can prove that it is a length preserving. See, these are the two properties that I have taken from Harvard University, right? From Harvard University. So, orthonormal transformation preserve length of the vector as well as the angle between them. Okay. So, can you prove this? So basically, I want to prove these two lengths are same. So let's just prove, okay? Let's just prove. First property, which is length preserving. Actually, both properties, length preserving or the angle preserving, both properties are actually very, very simple to prove. You just need to use the formula u into u transpose into u equal to identity, or u into u transpose, whatever suits for you, equal to identity. Okay. Using this formula, we can easily prove. How? Let's just see u into x. Okay. Length of this. Let me take square of this. Okay. That is nothing but length of this vector. Basically, this vector dot product with its own vector, right? This is the dot product. This dot is basically dot product. Okay. Uh, I mean, you can consider this as a matrix, I mean, this is a basically dot product. So, which means that the formula you might be knowing for the dot product, which is, but it is not needed here. A dot B equal to A length of A into length of B into cos theta. Do you know this formula? Dot product between two vectors. Anyway, this orthogonal projection, dot product, this regarding the vectors, actually we will have one class, but I'm just asking you if you know this. Okay, dot product between two vectors. Anyway, let's just not worry about it. But yeah, this is a dot product which is ux into u transpose x into ux, right? Okay. Now, now this is same as x transpose u transpose u into x. Okay. X transpose u into x. And since u transpose u is identity, so that is why this is same as x transpose x, which is same as length of x square. Okay. Length of x square. So which means from here we can say that length is anyway always positive. So let's not worry about plus minus. So basically length of ux is same as length of x. Okay. I mean, very simply, we can use this particular property and then we can prove that it is length preserving. So which means you take any vector, you multiply by orthonormal matrix. Okay. So u is here orthonormal matrix. Then length of that vector doesn't get changed. And the second property is it is angle preserving also, right? So let's just prove this property also. Okay, Mittal is asking me to explain this. Actually, I quickly told about it because anyway, like after the SVD, I'm going to anyway having one lecture specifically related to the vector and the I mean things related to vector. For example, length of the vector, projection of a vector into onto another vector, orthogonal projection, these things. Okay, so there you will get to understand that how to calculate the length, what is this dot product. Okay, and a projection of a vector onto itself and these things. Okay, so these things I will anyway explain. For now, just take it as my words that okay, this length square equal to nothing but a vector dot product by itself. Okay, I mean you can easily prove it also. For example, length of any vector v is nothing but, let's suppose v is v1 v2 v3. Then what is the length of this vector? It is nothing but square root of v1 square plus v2 square plus v3 square, right? So length square is nothing but v1 square plus v2 square plus v3 square, right? Now this is actually same as if you do the dot product between, if you take this v transpose and then dot product, you just consider just like a matrix. Okay, you consider this as a matrix, you consider this as a matrix. So which means it will be v transpose is nothing but v1 v2 v3 multiplication by v1 v2 v3, right? Okay, so this will be same as v1 square plus v2 square plus v3 square. So as you can see, this quantity you can understand it just like a matrix. Okay, this is a matrix and this is also the matrix. Okay, let's not worry about this dot. So this is a matrix, this is a matrix. Okay, so these two matrix product is nothing but v1 square plus v2 square plus v3 square, which is nothing but length of v square also. Okay, so that's why these two numbers are actually same. So that's why here instead of writing like this, I'm writing like this. Okay, just consider this is a matrix of one dimension. Okay, I mean, this is a row, okay, of one dimension, which is, you can say, 1 into n cross matrix. Okay, this is n cross 1 matrix. These two you can consider like a matrix. So basically these two numbers are same. Okay, so that's why I have written like this. Okay, so, but don't worry, this is just a short explanation. I'm going to spend one lecture just on the vectors. Okay. Specifically, if you remember in the Gram-Schmidt algorithm, I was saying that there's an orthogonal projection. These things are needed, right? So, orthogonal projection, length of a vector, okay, projecting a vector onto another vector, distance between a vector and the hyperplane, and these things. Okay, these things are actually necessary for machine learning also. So that is why it is better to understand these things in the linear algebra itself. Okay, but in the flow I started SVD because, like, I mean, we started uh, from linear transformation. From the linear transformation, I motivated the idea of similar matrices. How? Because similar matrices are, can anyone tell me in context of linear transformation what is the similar matrices? In the context of linear transformation, it is doing the same transformation in the different bases. Okay, similar matrices does the same transformation in the different bases, right? Do you recall this? Then from the similar matrices, actually, the diagonalization idea is there. And then from diagonalization, it is like eigenvalue decomposition. And from that, I started SVD. Okay. In this flow, I wanted to cover. So that's why I covered in this flow. But don't worry, regarding the vectors, we will be having one lecture. Okay. Cool. So I think this is okay to everyone that it is length preserving. Okay. Which means that that if you have any vector x, you multiply by orthonormal matrix, then the length of that vector doesn't get changed. Okay. And it is also angle preserving. So let me just copy this. It is also angle preserving. So let me just explain you that what does this angle preserving mean? Okay. And how orthonormal matrices are angle preserving also. So as I explained you, that angle preserving basically mean that if these are the two vectors, then whatever is the angle currently, if even if you multiply by u, then the angle doesn't get changed. Okay. So can anyone prove that orthonormal matrices are angle preserving? How to prove it? See, actually, so there is a formula you might be knowing, you might not be knowing. If you don't know, don't worry about it. We will cover this soon. But there's a formula that A dot B equal to length of A into length of B into cos theta, right? Okay. So if you do x dot y, then it is actually same as uh, x dot y is basically nothing but x transpose y, okay, or y transpose x, whatever. So if you do x dot y, it is actually same as ux dot uy, okay. Dot product are actually same. Let me tell you why. Let me tell you why. See, this ux dot ui is nothing but you can say ux transpose into uy. Okay, I mean, this dot product you can write it in terms of the matrix. Okay, you can remove this dot and then you can write as a matrix product. Okay, so these are the two matrices, you can understand like this. These are the two matrices. Okay, so these two are same. Now that is equal to x transpose uy, which is nothing but x transpose y, right? And x dot y is nothing but actually by the definition, as you can see, if you want to remove this dot, if you want to convert in as a matrix notation, it is x transpose y only. So basically this is anyway x transpose y, or maybe you can understand like this. We have started with this, right? Ux into uy, ux dot product with ui, and we finally found out this is same as x transpose y or x dot product with y, right? So basically x and y dot product and ux and uy dot product are same. X and y dot product actually mean length of x into length of y. Okay, this is normal multiplication basically. Okay, because these are scalar into cos theta, right? So This is the dot product formula. If you know, that's okay. Otherwise, you can for now, don't worry. We will have one class just for the vectors. This is length of ux into length of uy into, let's suppose this is cos alpha, and let's suppose this is cos beta. Since this and this are same, right? We have already proved that length is same. So this and this is same. Similarly, this and this is same. So from here you can say cos alpha equal to cos beta, which means alpha equal to beta, right? Okay, which means alpha and beta are same. So basically, if you multiply, okay, for now you can take as my words. If you multiply any orthonormal matrix, let's suppose this is theta, then then it it will only do the pure rotation. Okay, only. So orthonormal matrices, you can see, it will orthonormal matrices, normal matrices doesn't scale. Okay, doesn't scale anything. And orthonormal matrices, if I mean length doesn't change, which means it doesn't scale anything. And also orthonormal matrices do the uniform rotation, in the sense, if it is rotating by some theta 1, then it is also rotating by theta 2, so that ultimately it is theta, which means you can see that if you multiply by u, then what you will be getting, see here, if you multiply by u, then you might be getting something like this. So what is this? This is ax, or maybe ux. Okay, let me represent by u. This is uy. Okay, so which means orthonormal matrices, you can see, is basically does does pure rotation, that too uniformly, right? Okay, doesn't change the length, and also doesn't change the angle. Okay, so for example, let's take one example here. Let's suppose that these are the v1 and v2 are the, let's suppose, two vectors. Okay, if you multiply these two vectors, where v transpose is nothing but, let's suppose this is v1 transpose, this is v2 transpose, and I mean there are many other vectors, but that's fine. Okay, let's just, I mean, for example, I'm just taking two vectors here. Okay, you can take any random vectors, but I'm just taking specifically v1 and v2 to multiply with v transpose. Tell me, resultant will be, let's suppose this is, since it is a, I can say b1 and b2 are the length one, so I can say it is a unit one circle. Tell me, what will happen to v1 and v2? Will they get stretched? Will they get shrinked or something like this? Will this happen? No, right? So basically, if you multiply by V transpose is orthonormal matrix just like V. So if you multiply by that, then what you will be getting? You will be again getting a circle only, right? I mean, the vectors doesn't get scaled; they get only pure rotated, which means you will be getting a circle only, but the vectors will be rotated. By the way, how much rotation is there? You can also, figure it out. For example, can you tell me, if you multiply by V1 here, what you will be getting? So this is V transpose. If you multiply V transpose by V, what you will be getting? V1. I think if you multiply by V1, then it is 1 0 0 0 0, right? Like this, which is what we call E1, right? Is this okay to everyone? So basically, I mean, you can also tell the rotation. How much is the rotation? It is basically V1 is getting transferred to E1. So you can basically see here that this V1 will be E1 now, and V2 will be E2, right? So which means that V1 will be here and V2 will be here. So these are the two new vectors we are getting. And what is the length of that? Same, right? Same, which is unit. So what I'm trying to say, that if you have these two vectors as specifically, if you multiply by this orthonormal matrix, then what will happen? They will just get pure rotation. Okay, pure rotation. There is no shrink, there is no stretch like this. Okay, pure rotation, that too uniformly. So B1 will get, if they're orthogonal now, if they're orthogonal now, then will they be orthogonal after the multiplication? Tell me. Yes, right. So they will be orthogonal after multiplication also, right? So I can say if they're orthogonal now, then they're orthogonal after the multiplication also. And what is these vectors? This is E1 and E2, but that's fine. Okay. So the new vectors that we have got are E1 and E2. Now, what is the next matrix that we need to multiply? If you write A equal to U sigma V transpose, what is the next matrix you will multiplying? After V transpose, I think we will multiplying with sigma. Since sigma is a diagonal matrix, that is why it will not rotate. Okay. I mean, if you have any set of matrix, okay, if you might remember, right? U1, U2, you might remember that U3. If you multiply, let's suppose sigma 1, sigma 2, sigma 3, right? Like this. Then resultant will be just like sigma 1, U1, sigma 2, U2, right? I mean, basically, if you multiply any vector, or maybe you can say something like this. For example, if you like, you have any sigma 1, sigma 2, okay? And then you multiply any vector x. What is the answer? So I think, yeah. So what is the answer you will be getting here? So basically, yeah. So let me write this as x1, x2 instead of x. Let me write this as x1, x2. Let's suppose this is sigma 1, sigma 2, sigma 3. Then you will be getting sigma 1, x1, right? And then I think this will get multiplied by this. You will be getting sigma 2, x2, sigma 3, x3. Yeah. So basically, if you're multiplying a vector, right? Now, if you're multiplying these vectors by the, let's suppose first you multiply by the V transpose. Now you're going to multiply by the sigma. So each of the dimension, right? Each of the dimension uh, will get basically scaled, right? There is no, you can say there is no rotation or something. Is this interpretation correct, or we are missing something? Yeah, if the singular values are zero, then that's fine. Some of the values will be zero. If that is the case, right? Okay. If the singular values are zero, then some of the values are zero. Yeah. So basically, the vector will get scaled, right? So this particular vector will get scaled, and this particular vector will get scaled, right? So these are the two vectors. Specifically, these are the, you can say, the vectors um in the standard basis. I mean, this is E1, right? So specifically, if I take E1, then it will be sigma 1, right? The coordinate will be sigma 1. If you take E2, then the coordinate will be sigma 2. So basically, the circle is getting changed to, I can say, ellipse, right? The circle is getting changed to ellipse. Now, what are the next matrix you will be multiplying? You will multiplying to U, right? The next matrix you will multiplying is U. So if you multiply by U is again orthonormal, right? U is again orthonormal. So this is also, I can say, orthonormal. So it will do what? Tell me, will it change this, length? Will it change from, for example, this was circle. If you multiply V transpose, has it changed from circle to ellipse? No, right? So basically it will just rotate, right? So it will just rotate this ellipse. So it will just rotate. So finally, the ellipse might look like this, right? And this is the same thing that we will be getting if you directly multiply any vector by a. Okay, so if you have any vector x here, you can multiply that x by a, then you will be getting the same thing. Okay. So anyway, like what I'm trying to say here is that you are first rotating. Okay, so orthonormal matrix you can assume just like rotation. Okay, just like a pure rotation, and then first you're rotating, stretching, and then again rotating back. Okay, now let's just understand this even more. Okay, let's just understand this even more. Suppose suppose you have, let's suppose you have uh, a vector here. Okay, let's suppose sigma 1 and sigma 2 are two singular values that I have. Sigma 1 is, let's suppose, 2, sigma 2 is 3. Okay, let's suppose you have some unit vector here. Okay, some unit vector w. Okay, I mean this is a unit circle, right? So I'm just taking some unit vector w. Then the w, I mean, will be somewhere here, you can say. So basically w will get rotated. Now this ellipse, right, this ellipse, oh sorry, this circle is getting changed to ellipse. Now you tell me, if this is, let's suppose, again w. So as you can see this ellipse, what is the, let's suppose, okay, sorry, this sigma 1 is, let's suppose, 3, and sigma 2 is, let's suppose, 2. Okay, so this is 3, 2. If you see this ellipse, let's suppose this is 3, this is, let's suppose, 2. Okay, now what do you think the length of w is? Will it be greater than 3? What is the minimum length of this w? Could be as good as this sigma 2, right, which is 2, and could be as big as this 3, right? So the w, length of the w, we will prove it mathematically also, but for now I'm just saying length of the w will be less than equal to 2, less than equal to 3 if initial length, right, initial length was 1. Then after multiplying by v and then sigma, right, after these two multiplications. Okay, so see, after once you multiply v, will the length change? V transpose from here to here, will the length change? No, right? From here to here it won't change, that is for sure. Okay, from here to here it won't change. Now from here to here, what will happen? The length will change. Ultimately it will get stretched, right? Some of the dimensions will get stretched. So the first dimension, as you know, for any a vector, the first dimension, as I shown you, if it is w1 w2 before, then can you tell me after multiplying by this, it will be sigma 1 w1 and sigma 2 w2, right? Something like this, right? Something like this. Okay, so basically you can see from here. Let's suppose let's suppose if I say something like this, that I'm getting from w1 w2 to sigma 1 w1 and sigma 2 w2. Let's suppose I'm getting something like this. Now suppose for example sigma 1 is greater than sigma 2. Suppose this is 3, this is 2. Okay, then it will be, is this okay to everyone? Is this okay? Let me know. Right now, suppose, I mean, just for the hypothetical case, suppose that this is also 3. I mean, if at max let's suppose it is as good as sigma 1. Then if this is 3, then you can say, okay, or maybe, how do I represent? Basically I want to say something like this. See, if this is also 3, right, if this is also 3, then you can say at most it could be, let's suppose this is at most 3. Okay, so basically length of this is actually, obviously if you're multiplying by 3, it will be greater, right? So this is something like this. Is this okay to everyone? I mean, see, this is some length. I don't know whatever is the length. Okay, let's not worry about it. Okay, w could be, let's suppose, to start with, it need not to be unit. Okay, for example, it could be some vector. If you multiply with this, then you are getting sigma 1 sigma 2. If this is 3 2, then instead of 2, if I write 3, then obviously length will be bigger of this particular vector, right? And similarly, just for the sake of example, I'm saying to you, similarly, if you know, take everywhere lesser, for example, if you take everywhere lesser, which means, if you take instead of 3, if you take it less, then obviously the length will be lesser, right? So basically, can you say something like this? Is this okay to everyone? Intuitively it feels like it is okay, right? I mean, if you have some number which is greater than this number, then obviously the length ultimately it is contributing just 2, it is contributing 3 to some dimension, so ultimately it looks like that obviously this length is greater, right? Similarly this length is lesser. Okay, so basically what I'm trying to convey here is that this is 2 into w, length of 2 into length of w basically, right? This is 3 into length of w. So basically this is actually like the w that we have got, right? Which is 3 to w1 w2. This is the real w that we have got, and this is 2 into the old w, this is 3 into the old w. So what do you see from here? What do you see from here? See, this 2 is nothing but sigma 2 or some sigma, right? This is sigma 1. So you can see that if you're multiplying, right, then the maximum if all sigmas are as good as 3, if all sigmas are maximum as good as sigma 1, okay, or the maximum, then ultimately at max you will be getting 3 into that w. Okay, if all sigmas are very less, then it is 2 into that w. So what I mean to say, maybe it is little confusing, but what I mean to say, let's suppose you have sigma 1, sigma 2 to sigma m in that order, which means generally we write in that order only. Okay, I told you multiple times that we write in that order only. That sigma 1 is greatest. Okay, so if I'm writing that order, then can you tell me if I multiply sigma, okay, a matrix with a vector w, then this is, I can say, the new vector, right? See, this is the new vector. This is old vector, I can say, right? This is the old vector. So if I talk about the length, okay, length between the old vector w, and the new vector, right? New vector. So I can say that that the new vector length, okay, the new vector length will be in between like this. Let me know how many of you agree with this. This is the new vector. Its length will be Let me just write it, and then I will ask you people that how many of you agree with that. So basically, is this font okay or this is very less? You can see, right? Let me know. Okay. So this is basically, I can say, let's suppose the lowest sigma, okay, whatever the lowest sigma I have, sigma m, this is highest sigma, let's suppose sigma 1. Is this okay? The new vector length will be actually something like this, right? Something like this. It will be old vector length into the lowest sigma, because if everything is trimmed down to very less, then the lowest possible bound I can have is something like this, the highest possible bound I can have is something like this. Is this okay? How many of you can digest this? Okay, great. So Ajay Srinivas, Mitali, Yash, Thakkar, everyone is saying that okay, they can actually understand that is okay. So let me explain you why that is okay. Because if you take, see, if you take everywhere lesser, I mean, in fact, this 3 is lesser than, the lowest is 2, let's suppose in this case, right? If you take lesser, then this is something like this. If you take higher, everywhere, then it is something like this. So basically, the length of the new vector, if you multiply by the diagonal matrix, then the length of the new vector will be at most the highest, diagonal entry and the lowest diagonal. I mean, it will be in between that, right? Understood? Okay. So let's just solve one question. Probably you will get to understand little more. Okay. For example, let's just solve this question. Can you tell me this is true or false? Okay. Just solve these two questions and let me know. Okay. This is just a true false question. Okay. So many of us, you are saying false and then true, right? So I think Yash is saying false and then true. And then Ajay, let me just paste your answers. Mm. Okay. So what this question is saying, that if A is a matrix of singular values 3 and 5, okay. So now A is a matrix, like is A diagonal matrix? I mean, they claiming that A is a diagonal matrix? No, they're not claiming, right? They're not saying A is a diagonal matrix. A is just a matrix, right? Then there's just some W. They're starting with the unit W, that's fine. And then they are saying that the new W will be having the length AW will be 2. Is this even possible? See, the U and V won't do anything with the length. Only thing that is going to do with the length is sigma, right? Sigma will only deal with that length. Then minimum length should be 3, and I think maximum length should be 5. So, is this true? No, that is not possible, right? So, I mean, for if then there is some W, no, that is not possible. So, I think this is false because U and V won't do anything with the length. Only sigma will do, and sigma is a diagonal matrix with 3 and 5. Is this possible? Yes, this is true. Okay. Hope you understood. So basically, what they are trying to say is that if you have any vector w, you multiply by the sigma, then the minimum and maximum length will be given like this, right? See here, if you multiply this by sigma, this is sigma 1, sigma 2, sigma 3, right? Like that you will be getting. Then the minimum will be if everything is sigma 3, and maximum will be when everything is sigma 1, like that, right? Okay. So finally, I think we have got something like this, that U and V don't do anything with the length. So what is the main matrix that plays with the length? It is sigma, right? Okay, I hope you understood this, right? Now the singular values will tell you that how much length is going to get changed, right? The singular values, which means sigma 1, sigma 2, sigma 3, are actually going to tell you that how much it is going to change. Okay, you just tell me one thing. You just tell me one thing, that can you tell me, okay, can you if I give you, if I give you let's suppose this is the diagram, okay. If I give you V, okay, whatever is the V, I mean, if I give you numerically that this is the V, right? Suppose someone give you V, that this is the V. Can you tell me that can you find out that how much angle we rotate, with how much angle we rotate? Can you find out? Or maybe V transpose rotate. Let's suppose V is do you have anything in mind, like an orthonormal matrix, maybe 1 2 -2 and 1. Suppose this is V, with how much angle do you think it might be rotating? I mean, can you find out the way, how to calculate that way, how to get to know that V is rotating with this much angle? That's easy actually, if you just think about it. See, one thing is for sure, it does the uniform rotation, right? So you just need to find out how much it is rotating, for example, v1. How much it is rotating v1. See, initially it was v1. Initially it was v1, for example, and then ultimately it is just a standard basis vector which is even, isn't it? See, initially it is v1, but ultimately even. So it is going from v1 to even. It is going from v1 to even. So you just need to find out the angle between v1 to even, isn't it? Or v2 to e2, okay, whatever suits you, okay, or v2 to e2. So you just need to find out the angle between, or you can say v2 and e2, right? Like in that way you can actually get to know how much it is rotating, okay? Or v2 and e2. Is this fine to you guys? Okay. Okay. So basically, I mean, currently, let's suppose we don't know how to find out the angle, and this we will see just after the SVD. Okay. So this we will see little later. I mean, in just 1-2 class. But for now, I hope you actually got the idea that, okay, if you actually have to find out that how much V is rotating, you just need to find out that what is the angle between V and E1, right? V1 and E1. Okay. Okay. That's fine. Now suppose you have to find out how much A is rotating. Then how much A is rotating. So basically, ultimately, how much this A is rotating. Suppose you have to find out this. Then probably you have to find out that how much this V transpose is rotating, right? Sigma won't rotate anything. Then how much this U is rotating? If they're rotating in the same direction, then add, otherwise subtract, right? Like that, right? I mean, this is just one idea, but we will see the rotation matrix and these things later on. Okay, we will see some rotation matrices. But yeah, is this idea clear? Maybe you have to first find out that how much V is rotating, V transpose is rotating, and then you have to find out how much U is rotating. If they're rotating in the same direction, then maybe add, otherwise subtract, and so on, right? I mean, this is just one thing that I'm telling you. We will see in future. Okay, rotation matrices we will see in the future. Cool. So basically, from this picture, it is very clear that U and V just rotate, doesn't change length, and sigma is something which change the length, right? Which change the length. How much it change? Maximum it can change, but the maximum is singular value. Minimum it will be changing with the minimum singular value, right? Okay. Now let's just discuss few questions on SVD. Okay, few questions on SVD. Let's just see few of the question, and after those questions, you will be basically feeling more confident in SVD. So we are going to see 30 questions now. Okay, so this is a practice set solution, which means that we will solve 30 questions. Maybe in today's lecture we will solve all the questions. Otherwise, we will take some of the questions tomorrow. Okay. Okay. So what they're saying, find the eigenvalues and singular values of this matrix. So how to do it? The singular values, as you know, right, are the basically eigenvalues of A transpose A. So see, I think this is, yeah, this is upper triangular matrix. So eigenvalues are anyway 0. Okay. So this is upper triangular. So these are the eigenvalues, right? And what are the singular values? You just find out A transpose A, and then this is also diagonal. So the singular values are just 1. Okay. I mean, repeating 3 times. Okay. Let's just see this question. So what they're saying is that suppose something like this is given to you. I mean, some SVD decomposition is already given to you. Now they are saying which vectors Vi are in the null space of A, which vectors Ui are in the column space of A. Just tell me what is the answer here. This is easy question only. You should not be taking much time here. Yeah. So Harsh is saying V3 is in null space. Okay. So V3 and V4 is in null space. Okay. So let's just see. See, I think these are the two non-zero singular values, right? Non-zero. So since these are the non-zero singular values, that is why you will say the U1, U2 are in the column space, right? Or yes, more specifically, they are bases for the column space. Okay. So basis of column space of A are actually U1, U2, right? Basis of column space of A. Now, what is basis of null space? Actually, uh, apart from V1, V2, you will be starting from V3 and V4, right? So V3 and V4. Yes. So every one of you are correct actually. Okay, great. So I think most of you have given the correct answer. Let me paste it. Mm, just a second. Let me make some space for answers. Okay. Now let's just go to the next question. So I think this is okay. Let's see this question. Okay. So what they're saying that suppose that age some singular value decomposition which is already given to you. Now they're saying find the eigenvalues of A transpose A, find the basis for the null space of A, basis for the column space, singular value decomposition of minus A transpose also. Okay. Do you want to try this quickly? Just let me know the eigenvalues of A transpose A. So eigenvalues of A transpose A must be 1 and 4 or 1 square and 4 square or maybe 1 and 2. Yes. So basically this is sigma, right? These are the sigmas. Eigenvalues are actually sigma square. So you can say it is 1 square, 4 square. Is this fine or should I be writing more? Tell me. Are these are only eigenvalues? Are these only eigenvalues? See, A is basically the same dimension as sigma, right? A is you can say this is 3 cross 1, 2, 3, 4. So 4 cross 3 into 4 cross 3. So I think there are 4 or there are 3. How many how many eigenvalues will be there? A is of what dimension? 3 rows and 4 columns. So A transpose A, it will be having 4 cross 4, right? So I think there are 4 eigenvalues. So what are those? Yes. So these are the 4 eigenvalues, right? Non-zero are 1 square, 4 square. Other than that, these are the zeros. Okay. Find a basis for the null space. What are the basis of null space? I think initially you have column space, then V transpose. Let's suppose what is the column space? I think these two are in the basis for the column space. And then 3 and 4, right? Then I think V1 transpose, V1, 3 and 4. Okay. So I think this is right. Yeah. Last two columns or last two rows? Tell me. Are these or these? Of V. Of V, you tell me. Of V. Okay, just think about it. See, see, let me walk you through the diagram. See, this is V transpose, right? So these are the rows of V transpose, basically, you can say, right? Rows of V transpose. For V, if I talk about the null space, these will be the columns, right? So for V, it will be the columns. If I talk about the null space. So last you can say two columns. Okay. For V transpose, these are the rows. That's why for V, it will be the columns. Okay. So it might be a little confusing, but see here that you write V transpose here, right? V transpose means this is V1 transpose, right? Now, if you take one more time transpose, this will be V1, V2 like this. So these are the columns of V. Okay, rows of V transpose, but columns of V. So what is the answer? Last two columns of V. Find the basis for null space of A. Sorry, this was the null space only. They're asking. Okay, this is null space. They're asking column space. For the column space, what is the answer? Yeah, first two columns of V, U, right? First two columns of U. Yeah. And let's just find out the singular value decomposition of minus A transpose. So if A is U sigma V transpose, then A transpose will be V sigma transpose U transpose. You just multiply by minus, right? You can just multiply by the minus. So, so where will this minus go? Will you be writing this minus with this or with this or with this? I think you can write with the uh, any of this. Okay, it is okay to write with the any of this. So it will be, yeah, because see, if you multiply the minus with the sigma, then the eigenvalues will change, right? So actually, it is not just about the minus. Any scalar multiplication, you if you write it with the sigma, then the eigenvalues will get changed. You can't change the eigenvalue. See, if x is the eigenvector, then can you say kx is also the eigenvector? Tell me, right? So basically, multiplying the eigenvector with k is okay. So you can multiply by minus here. Okay, let's just see the answers. Yeah. So basically, u equal to minus v. So they are multiplying minus with b. Okay. Let's now see this question. Show that if A is a square matrix, then determinant of A is a product of singular values of A. So let's just see this. If it is a square matrix, okay. By the way, what is the I can say what is the SVD of this? Okay. Now, if you find out determinant of this, then it is a product of singular values of A. Okay, just let me know. Just try this question and let me know if you are able to solve this. Yes is saying U is 1, V transpose is diagonal determinant. Okay, so let's just see this. See, we have already proved one thing. Okay, you might remember that determinant, let me just go to that slide. See here, determinant of any orthogonal matrix, orthonormal matrix, sorry, any orthonormal matrix is either plus one or minus one. It's very easy to prove, right? Very easy to prove. So we have proved it. So we can take help of this. So let me tell you how. So see here, We have already proved it. Now what we can do, we can find out determinant of this A. What is the determinant of this A? It will be determinant of U multiplied by determinant of sigma multiplied by determinant of V transpose. And interestingly, we know either this is +1 or -1. This is nothing but product of, I mean, you can say product of the singular values, right? So this is nothing but the product of singular values, right? This is again +1 or -1. So ultimately, you can say it is just, +1 in or -1 into product of singular values. But if you take modulus of this, okay, if you take modulus of this number, determinant of A, then this is just the product of these values, sigma 1, sigma 2 till sigma n. Okay. If you take modulus, because plus minus 1 will be just +1 here. Okay. So Bachu Paul is asking that for square matrices, sigma and lambda are same. Is this true? Is this true? Let's just see. So for square matrices, just tell me, is this true that sigma and lambda are same? So it is actually very easy to prove that this is false. Okay, this is false. Why that is the case? Let's just see some counterexample here. I think we can produce some counterexample easily. What is A transpose A? This is, if you multiply 1, 0, 0, 0, what you will be getting? Okay, for this, you're not getting that. If you have, let's suppose, but it is actually very easy to see using the determinant itself. So the determinant you will be getting, right? Determinant of A is actually plus minus, right? Plus minus of this thing. Okay. It will depend on determinant of U. But in terms of the eigenvalues, it is just, product of only eigenvalues. You don't have plus minus there, right? So from there also it is easy, but let's just see if we have any other counterexample. So this is basically 1, 1, 0, 0. If you multiply these two, you will be getting 1. This multiplication, this is 1. This is again 1. Okay, this is again 1. So this is, let's suppose, A transpose A. Okay, this is A. This is A transpose, let's suppose. So you find out the eigenvalues here, okay, and which is the singular values, and you find out the eigenvalues here. So I mean, you calculate for this square matrix. Most probably, I think the singular values and eigenvalues won't be same. Okay, I'm just picking a random example, but I think it won't be same. Okay, for this particular example. So, for example, if you find out the eigenvalues, it will be something different. If you find out the singular values using the eigenvalues of this, then it will be most probably different. Okay, cool. So let's just go to the next question and let's just see that what is that. Okay, let's just see this question number 6. So this question is easy question. If you want, you just give a 1 minute here and you just try it out. Okay, just let me know what you are getting. Okay, so this particular question is a nice question. Let's just see. Okay, so what they're saying that every real matrix has SVD. So I think that is true. So this A is true. Let me mark this is true. Right, this is true. If because SVD is unconditional, right? If a matrix Q is orthogonal, then its singular values are 1. So what do you think about it? See, if it is orthogonal, then what is the single value decomposition? I think it could be itself, right? I mean, this could be identity. This is identity. I mean, the sigma and U or sigma and V transpose both could be identity. So yeah, this is 1, right? This is 1. So I think this is also true. Okay. Are there other arguments for this? Ajay has given very nice geometric interpretation of this particular question. So let me just put it. So Ajay is saying something like this. Okay. So what he is saying is that orthonormal matrix should not change the length. I think this is length. Should not change the length. Okay. Singular values has to be. So basically, singular values decide the length, right? Ultimately, the singular values decide the length. And since they do not change the length, that's why the singular values are one. That's awesome. I mean, that's very, very nice interpretation. Okay. I can say it's really good. Okay, very good. This is how geometrically he has explained. That's, I think this is the kind of explanation if you give in the interview, then the interviewer or the professor will be so much happy. Okay, he will almost take you. Okay, if you don't mess up with the other questions, then he will definitely take you if you give these kind of interpretation to the interviewer. Okay, that's really very, very good, I must say. Okay, a matrix R will have exactly R singular values greater than 0. So, matrix with the rank R. Yeah, I think yes, right? So, 1, 2, 3, all are true. Okay. Let's just see this question. This is question number 7. Let's just see this question. So, what they're saying, the singular values of any square matrix is absolute value of eigenvalues. I think this was something that almost similar that Bachu Paul has asked, right? So, it is actually false. I mean, you can have the counter example. For example, okay, they have given this as a counter example. 0, 1, 0, 0 has singular value of 1, but the eigenvalues are 0. Actually, there is no relation. Okay. So, for example, 0, 1, 0, 0. If you find out the singular values using the eigenvalues of A transpose A, then the singular values, sigma, is basically 1, but the eigenvalues are actually 0. Okay. So this is actually false. What about this? The number of non-zero eigenvalues of a square matrix is equal to number of non-zero singular values. What do you think? This is true or false? Yeah, this is true, right? So number of non-zero eigenvalues are nothing but square root of the singular values. So these two are actually same. So this is true. Sorry, what they're saying? Number of non-zero eigenvalues of square matrix. Oh, they are saying eigenvalues of the matrix itself. Okay, that's interesting. That's, I think, false, right? So here the eigenvalues, as you know, eigenvalues are actually 0 and 0, but the singular values is 1 and 0, right? Yeah. So I thought they are talking about A transpose A. Actually, there is no relation between the eigenvalues and singular values. Okay. So the number of non-zero eigenvalues and number of singular values are actually, I mean, these are actually false. I thought they are talking about the eigenvalues of A transpose A, but eigenvalues of that matrix itself, then this is false, right? I mean, the counter example is first. Same counter example as above. The eigenvalues of A square are the square of eigenvalues of A for A square. I think this is true, right? Okay. So it seems like it is true. This is EG. The singular values of A square are the square of singular values of A. Do singular values also have the same thing? If A is U sigma V transpose, then A square will be uh, will be having the sigma square in between. Let's just see. U sigma V transpose into U sigma V transpose, right? I don't think there is any relation. If A is this, then what is the A square, by the way? 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay, this is the counter example, right? Okay, this is a very nice counter example. So basically, if you take this as A, then A square is a zero matrix actually. It is a zero matrix. Then eigenvalues and singular values, everything will be just zero. Sorry, the eigenvalues will be zero, at least of this zero. And A eigenvalues is anyway. Okay, sorry, A eigenvalues is anyway. They're talking about singular values. I'm sorry about it. So the singular values of A are 1 and 0. What will the singular values of zero matrix? This is diagonal matrix, right? For the diagonal matrix, SVD is very easy. How? This is the, you can say this is the SVD. I mean, here you can take the identity. Here also you can take the identity matrix. Because identity is anyway orthonormal, right? You can put it as it is. So what are the singular values here? 0, 0, right? I mean, these are the singular values. Singular values here are 0, 0, but singular values of A square are 0, 0. But singular values of A, which is 0, 1, 0, 0, it is actually 1, 0, right? So the singular values of A and the singular values of A square doesn't have any relation. Okay, see, this is the singular values of A, and singular values of A square will be, you don't know, right? I mean, it will be some complicated. So it doesn't have any relation. Seems like it doesn't have any relation. The singular values of A inverse. Okay, let's just see the relationship between singular values of A inverse and singular values of A. So if A is U sigma V transpose, then A inverse will be V transpose inverse is just V, I think, right? Sigma inverse and U inverse is just U transpose actually. So I think this is true. Oh, great. Because here you got this, right? So this is true. Is this understood to everyone? This is true. Because you find out the singular value decomposition of A inverse. It is coming like this, right? So diagonal matrix means 1 minus sigma 1, sorry, 1 upon sigma 1, 1 upon sigma 2, like this, right? So this is true. Okay. Yeah, this is true. This was false. So you can check the answers later on. Okay. This question was a nice question. I've taken this from MIT. Let's see this question. Again, this question is from MIT. Let's see if you can solve this question. So they are saying that throughout this problem, the matrix A has the following SVD. Now they are saying where the U and orthogonal X and Y are two mysterious number. Okay, I mean they have not given what are these X and Y, which is fine. Now what they are saying, the matrix U and V include the prefactors 1 by 5 and 1 by 3. Okay, this is including U. This is including this V transpose. That is fine. Okay. What are the values of X and Y based on the information provided? Can you tell me what is the value of X and Y? It is easy with just, one interpretation. Should I give you the hint? This vector is, okay, this vector is, okay, I am not telling. Yeah, Paul has got the answer. Yeah, this vector is perpendicular to which vector? Yes. So it is perpendicular to this vector and this vector. So just using these two dot product, make it 0 and get your X. Similarly, get your Y, right? Understood? Okay. So basically if you do the dot product with first, you will be getting your x. Similarly, you will be getting your y. So Bachu Paul has given the correct answer. Okay, -2 and 1. Have you solved using the similar way or there is some other way? You can just tell me. Okay, great. Right? With just simple, observation, you can solve this question. Let's see next question. This question I've taken from some university. Right? Let's see this question, what they're saying. Let A is 2 by 2 symmetric matrix with the unit eigenvectors. If its eigenvalues are 3 and -2, what are the matrices U, sigma, and V in its singular value decomposition? Okay, this is a good question, I think, right? With unit eigenvectors are given to you. Symmetric matrix with the unit eigenvectors. Okay, it is a symmetric matrix. Since it is a symmetric matrix, you have the eigenvalue decomposition itself, right? So what is the eigenvalue decomposition? Do you remember? Eigenvalue decomposition looks like this. So A equal to U lambda U inverse, right? If it is a symmetric matrix, then this is same as transpose. So U is given to you, which is U1, U2, right? Since these are the unit vectors and these are corresponding to these two, do you think this is an orthonormal matrix? What do you think? Will this be the orthonormal matrix? If these are corresponding to different lambda in the symmetric matrix, eigenvectors are perpendicular to each other and the norm is also given to you. They are saying that these are the unit vectors, right? Since these are the unit vectors, that is why you can say that the length is 1. So that is why this is okay. This is 3 -2 and then U inverse is just U transpose. So it is U1 transpose and this is U2 transpose, right? So like that, you can get your A. Is this also the SVD? Tell me. Is this orthonormal? Is this diagonal? Is this orthonormal? Okay. So is this SVD? Tell me. Okay. Why this is not SVD? In the SVD, the eigenvectors of. Okay. So yeah. So you are saying in the SVD, take the eigenvectors of A transpose A, but here the here we are given for A. Okay. Yes, that is true. This is not SVD. Yeah, that is okay. So they're asking you to find out the SVD. Okay. So this is not SVD, that I agree. So how to find out the SVD? Maybe you can calculate A transpose A, right? So this was the eigenvalue decomposition. But if you calculate A transpose A, what it will be? Since it is symmetric matrix, this is just, A into A square. Or maybe you can also, multiply uh, A transpose A. Since it is symmetric, I can say it is A square. Okay, so the eigenvalues of A square will be just, I think 9 and 4, right? These are the eigenvalues of A square. Is this okay to you? So A transpose A is nothing but A because A is A square, because A is symmetric. So what are the eigenvalues of A transpose A? Is this okay to everyone? Right? Okay. Now I have the eigenvalues of A transpose A. We just need to know the eigenvectors of A transpose A, right? So what are the eigenvectors of A square? Can you tell me? Which is A square. So A square into X, let's suppose X is the eigenvector. Let's suppose AX equal to lambda X. So if you do A square into X, it is nothing but A into AX, which is nothing but A into lambda x, it is nothing but lambda into AX again, it is nothing but lambda square x. So basically you can see that x is the eigenvector only, right? X is the eigenvector only. I think we have proved it earlier also, right? In the eigenvalues, eigenvector lecture, we have proved it. So basically we know the eigenvector is x itself. Now we got the eigenvalues of A transpose A. We got the eigenvectors of A transpose A. Then how to find out the SVD? How to find out the SVD? You write down the eigenvectors, okay, of A transpose A. You write down the square root of eigenvalues, which is 3 and 2. Write down the eigenvectors of A transpose A, which is basically the same as the eigenvectors of A. So which is U1, U2. This is U1 transpose. Sorry, I mean, this is the same thing. You write down the eigenvectors of A transpose, right? A transpose, A transpose, A, actually both are same, right? So this is U2 transpose, right? So this is the SVD. Do you agree this is orthonormal by the given information? This is orthonormal, right? So we can find out the SVD, right? We can find out the SVD. I think this was a good question. Let's just check it. Okay. So what they're saying is that asymmetric, that's fine. And this, therefore, it implies okay. Besides U1 and U2 are the unit vectors. Further, we know that this is the case. Okay, they multiplied minus in this U2. Why you need to multiply the minus? I think minus should be multiplied because otherwise it is inconsistent with your eigenvalue decomposition. But why we are multiplying by the minus? We need to write the eigenvectors, right? Okay. Uh, they have to perpendicular to each other. So the eigenvectors of A transpose A. Eigenvectors of A transpose A are the same. Okay. So why they're multiplying by the minus? Can you figure it out? See here. Let me just check. These are the eigenvalues. Lambda square. Eigenvector is U1. And eigenvector is U2 itself, right? Uh, then they have got sigma 1 and sigma 2 is 2. Because U1 and U2 are the unit eigenvectors. Furthermore, we know that AU1 and AU1 is equal to lambda 1 U1. Okay. So let's just do it from beginning. See what they're saying. 3 and minus 2 are the eigenvalues, right? Let's just see that if we are missing something. So 3 and minus 2 are the eigenvalues of A. So what is the eigenvalues of A transpose A? It is just A square. The eigenvalues will be, you can say, here will be 9 and 4, right? Similarly, we need to find out the eigenvector of A transpose A, which is eigenvector of A square. It should be X, same as eigenvector of A, right? Okay. So in that case, I have the eigenvectors that is, orthonormal also, because have to be, okay, there are two different eigenvalues. Okay, I got it, I think. See, these are the two different eigenvalues. Here, you are getting the eigenvectors u1 and u2 has to be orthonormal to each other, right? Okay, Hertz is saying that, uh, okay, using this formula, ui equal to this, I mean, that is fine, but I'm just figuring it out that why we are going this way, then we are not getting the same answer as they have got. What do you think? These are the eigenvectors. I need to write eigenvectors of a square here, eigen and square root of the eigenvalues 3 and 2. Eigenvectors will be this also, will be multiplied by minus also, that's fine. I mean, the eigenvector is u also, u minus u also, that's fine. But they have taken minus u. I think we can take any of this because these both are the eigenvectors. Most probably both should work. I mean, there are multiple SVDs actually for given A, right? So most probably both should work. Let me just check more. No, A transpose A and A transpose both are fine in this case. Both are A square only because A is a symmetric matrix. Hers is saying about A transpose and A transpose A. So actually, A is a symmetric matrix. So that is why A transpose and A square A transpose A both are fine. Okay. So most probably, I think them. I think you can put u1 u2. You can also put, some multiple of u1 u2 also, because they are, oh, not multiple, because it won't be orthonormal. At least you can multiply with a minus, right? Should be okay to multiply with a minus, because I mean there are multiple SVDs possible. I will just check that is this minus really necessary, or we can just omit it. Okay, I will just check and let you know. Most probably, like, you can multiply by the minus or you do not multiply the minus. Both should be fine, because these are also the eigenvectors of A transpose A. Okay, or the A square. These are the eigenvalues. I mean, square root of the eigenvalues and then the eigenvectors. So I think both are fine because there are multiple SVDs possible. We will also talk about the uniqueness of the SVDs, that how many SVDs are possible like this. Okay, we will also talk about it. Okay. So now let's just do one thing. Do you want to try the remaining questions by your own? So there are, I think, 20 more questions. Okay. So there are 20 more questions. These are the easy questions only. Just try it out by your own and see. The answer is on the next page, and see if you're able to solve. Okay. See, the answer, the questions are not very tough. Answer is on the next page. You just try out these questions and see if you're able to solve. Okay. There are 20 more questions. And then we will discuss these questions tomorrow. Okay. Okay. Thank you, everyone. Thank you so much. Okay. Take care.